Let's look at logarithmic derivatives, and this is a fairly nice formula, but for some reason people have a hard time remembering it. Maybe some anxiety with logs, but if you have log of x, the derivative of log x is 1 over x times the natural log of whatever the base of the original logarithm is. So you have to remember that part. Usually we have just regular natural logs, which we'll talk about that in a few seconds. So there's your general formula. It's 1 over the inside, 1 over x, times the natural log of the base. So when we are doing the derivatives of logs and the inside is not a clean x, for example, down here where I have just some random function that we don't know what it is, that f of x is replacing x in the formula. So instead of 1 over x natural log b, this is going to be 1 over f of x natural log b. But the fact that the inside is now ugly invokes the chain rule. So I just did the derivative of the log part, 1 over inside times natural log b. Now I have to multiply by the derivative of that inside to complete the chain rule. And in the case of logarithms, instead of writing 1 over stuff times f prime, I will usually just stick that f prime in the numerator and make the derivative f prime over f times the natural log of the base. So let's see what happens if you have a natural log. Well, the natural log of x, well, that is a log. You just have to remember that natural log is log base e of x. And so if I follow the logarithmic formula for that, it would be 1 over x, 1 over the inside, times the natural log of the base. And in this case, my base of a natural log is e. So it'd be 1 over x times natural log e. But the natural log of e is 1. So the derivative of ln x is just 1 over x. That ln e technically is there, but because it's 1, we don't bother writing it. So the derivative of ln x is 1 over x. And when you apply the chain rule to that, the derivative of ln of f of x, you replace the x with the f of x, but then you have to multiply by the derivative of the inside. And again, like I did up here, I'm going to write that as f prime over f. And for the most part, we will be dealing with natural logs, not logs of other bases. So this is generally the formula we're going to be using the most, that the derivative of a natural log is the inside derivative over the inside. So let's look at a few examples, and these are relatively quick. So I see a logarithmic function. I notice that the base is 6, and the derivative of any logarithmic function, I know it's going to be a fraction. The argument, the inside of the log, goes in the denominator. So I have sine of x plus 1 in the denominator. The derivative of that goes in the numerator. The derivative of sine is cosine, and the derivative of 1 is 0. So there's the derivative of the logarithmic part, but because this is log base 6, I then need to put a natural log 6 in the denominator, and you are done. It's the inside in the denominator, the derivative of that on top, and then natural log of the logarithmic base in the denominator as well. Let's try another one. The natural log of x to the 5th plus 9x plus 2. Well, the derivative of every log, whether it's natural log or some other base, starts off as a fraction where the argument goes in the denominator, x to the 5th plus 9x plus 2. The derivative of that goes in the numerator, and that is the chain rule part of this. So 5x to the 4th plus 9. And then you always want to put the natural log of the base of your original. However, if you have a natural log, the base, this is log base e. So if you wanted to write natural log e down here, you could. However, natural log of e is 1, so we don't bother writing that. And I would only answer with this. That would be all I write down. Let's try another one. So here I have the tangent of natural log x, and this time I put the natural log on the inside. And so when I do the chain rule here, we have to recognize that this is initially a tangent function, then the natural log inside. So when I do the derivative of this, I start by differentiating tangent, and the derivative of tangent is secant squared. We leave the inside alone. And so I just differentiated the tangent part. Now we look inside, I see a natural log x. The derivative of natural log x is 1 over x. And there's your answer for number 3. So that is a chain rule, but the outside was trig, and the inside was the log. Let's see number 4. Another log. This is log. There's no base written, but you should know that log without a base written is log base 10. And so this derivative, my log's on the outside, so I'm going to start with the derivative of a logarithmic function, which is the denominator is the argument, so x cubed cosine x. And then the derivative of that goes on top, and the inside is a product rule. So this one, I'm going to do derivative of first. So 3x squared, I'm going to leave the cosine alone. Plus, now I leave x cubed alone, and the derivative of cosine is negative sine. So there is my, oh, nope, not yet, I'm sorry. So I did the derivative of the inside over the inside, and then you have to remember to multiply the denominator by the natural log of whatever the base of the original log is. So this is log base 10. So I multiply the denominator by the natural log of 10, and we're done. That is number 4. Now, the next one I want to look at is the exact same problem, because the way I just did number 4 is how a lot of people will dive into logs when they first learn how to do derivatives. There's nothing wrong with this, but that is incredibly ugly compared to what we could have done. And in precal and algebra 2, you learned some properties of logs that allow you to change the way this is written. And one of the properties was that if you are multiplying inside a logarithm, you can split that logarithm into the sum of the pieces being multiplied. So I'm going to change it to log base 3 plus, log of x cubed plus log of cosine x. And then I can go one step further, because another property says that if you have an exponent on your argument, you can pull that exponent down front. Now, don't get confused with this maneuver, because pulling that 3 down looks kind of like the power rule, but it's not. This is a property of logs that you learned in algebra 2. So I am not doing any derivatives yet. All I am doing is rewriting the original problem, which is why I am labeling it y equals y equals. I did not do the derivative. Now I'm about to do the derivative, dy dx. And so now I have 3 times log x. Well, if you have a constant times a function, you can ignore the constant and just do the derivative of the log. The derivative of log x is 1 over x, but you have to multiply by the natural log of the base. So that'd be 1 over x ln 10. Plus, now I'm going to do the derivative of log of cosine x. The derivative of every log, you put the inside in the denominator, and the derivative of that in the numerator, times the natural log of the base in your denominator. And this is, in my opinion, a much easier derivative than what I initially did on number 4. The only trade-off is we had to do a little bit of precal algebra 2 stuff at the beginning. I think it's worth doing that little bit of work at the beginning to make the derivative that much easier. I avoided the product rule in using those properties. So do remember these properties. These are the properties that you did learn in algebra 2. The log of a product can be log A plus log B. The log of a quotient is log A minus log B. And then if you have an exponent on your argument, you could pull that down in front of the log. In this case, I used natural logs just because it was easier to type, but it works for logs of any base, and we also will be dealing with natural logs more often than anything else in calculus. So that's another reason why I use natural logs there. So let's do a couple more. The natural log of e to the secant x. Well, if we dive straight into the calculus, you would think, okay, I'm going to put e to the secant x on bottom, because you should. And then the derivative of that would go in the top, and the derivative of e to the stuff is e to the stuff, it's a chain rule, e to the secant x, times the derivative of the exponent, which will be secant x tangent x. And you notice that the secant x's, e to the secant x's will cancel, leaving you with only the derivative of secant x tangent x. And the reason it cleaned up so nicely is because I, once again, kind of like in number 4, I skipped the early work that could have made the problem easier, and I dove straight into the calculus. You need to remember the properties of logs, and I'm going to break this one down really slowly, or in 2 steps, I guess. You can pull that exponent in front and make this the secant of x times the natural log of e. You can pull that exponent down front, and the natural log of e is 1. So this function really is just y equals secant x, and the derivative of secant x is secant x tangent x. So anytime you have a logarithm, if you ever see a log, automatically turn on that part of your brain that that is holding these properties and think how you can use those properties. And I am even going to add one more, and that is that if you have the natural log of e to anything, that will always simplify to just that anything. And that really extends to logs of any base. So I have log base b of b to the a power. That will clean up to just the exponent. And that's what I took advantage of here in number 5. See, how many more do I have? I think I have 2 more. Nope, 1 more. All right, so e to the y is equal to secant x. And there is a way you could solve this with implicit differentiation. However, that's going to make it a little bit more difficult than what I'm about to do. So instead of diving straight to the calculus, I'm looking at this and I'm thinking if e to the y is equal to secant x, I could introduce a natural log. The natural log of e to the y is just y. And I'm going to rewrite my function instead of e to the y equals stuff to y equals the natural log of secant x. And that to me is a very easy derivative because the derivative of any natural log, the inside, the argument goes in the denominator, and then the derivative of that argument goes in the numerator. So the derivative of secant x is secant x tangent x. And then once again, I can clean that up a little bit. The secants cancel, leaving you with just tangent x for your answer. So there are a few examples of logarithmic derivatives. Hopefully that made some sense to you.